Okay, so you know how LLMs are really smart,
Yeah,
but like sometimes they just kind of make stuff up
totally.
or they're stuck using information that's like totally outdated?
Oh,
Well, today we're doing a deep dive into like a possible solution for that. It's called retrieval-augmented generation, or REG.
right.
It's basically like giving these super powerful AI models access to the entire internet,
Yeah.
but in a smart way.
In a smart way, exactly.
Yeah.
And the cool thing is, like, for anyone who's really into like understanding how these things actually work, to make them better,
Yeah.
we've been looking at some research that gets into like the nitty-gritty of how to optimize these systems.
Nice.
And today we're mainly focusing on the very first step, which is the retriever. The part that goes out and grabs all the information that the LLM is going to use.
yeah, like finding the right information is so important.
It's crucial.
It's like the foundation of the whole thing.
Absolutely. And the sources we've been looking at, they really highlight how important it is to get that retrieval part right. Right?
Right.
Because it directly impacts how well the whole RJ system can answer questions, accurately.
That makes sense.
Yeah. And we're going to unpack some experiments that are trying to figure out how to build better retrieval systems.
Cool.
This includes not just getting the right answers, but also something called attributed QA,
Attributed QA.
where the AI actually tells you where it found the information.
Oh, wow.
It's like showing its work, so to speak.
That's super interesting. So if you're really into RGA and you want to make your pipelines like really sing,
This is for you.
this is the episode for you.
For sure.
Okay, let's jump in. So what's the basic flow of a RAG system?
Okay, so imagine you have a librarian
Okay.
who's like incredibly fast and knows where everything is.
Right.
That's kind of like the retriever in a RAG system.
Uh-huh.
It takes your question and searches through a massive amount of documents to find the ones that are most relevant.
Okay.
And the second part is the reader, which is usually the large language model itself. And it takes your original question, along with all those documents that the retriever found,
Yeah.
and uses that context to create an answer.
Okay, so it's like a two-step process.
Exactly, a two-step process.
Got it. So for this deep dive, we're focusing on that first step,
The retriever.
the retriever librarian.
Yeah, the librarian, exactly.
Okay, cool. So it makes sense that if the retriever brings back the wrong books, the answer's probably going to be off too.
For sure, for sure.
How did the researchers test what makes a good retriever?
That's a great question. So they didn't just rely on like gut feeling or anything.
Right.
They put these RG systems through some really rigorous tests.
Okay.
They evaluated them on standard question answering tasks.
Mm-hmm.
But what's really interesting is they also looked at attributed QA,
Attributed Q.
which is where the model doesn't just answer the question,
Yeah.
but it also tells you exactly which documents it used.
Oh, wow. So it's like showing its sources.
Exactly like a bibliography.
Yeah.
It's about building trust, making sure the AI is transparent.
That makes a lot of sense,
Yeah.
especially if you're using it for something important.
Absolutely.
So what kind of questions and information were they using to test this?
Okay, so they used a few different data sets that are pretty standard in this kind of research.
Okay.
One was ACE-QI, which is a set of real-world questions.
Real world?
Real-world questions that are often pretty complex and long form.
Okay.
And then there's QMPARI, which focuses on questions that can have multiple right answers.
Oh, interesting.
Yeah. And then there's natural questions, which is based on actual questions that people type into Google.
So like real searches.
Yeah, exactly. Real searches.
That's cool.
And for the information they were searching through,
Yeah.
they mainly used Wikipedia,
Okay.
different snapshots of it throughout its history.
Makes sense. It's huge and it's constantly being updated.
Exactly, constantly evolving.
So one thing that really jumped out at me was this idea of how many documents you actually need to retrieve.
Yeah.
You would think that like more is always better.
Right, it's a common intuition.
But is that actually true?
That's a great question. And it turns out it's not always the case.
Really?
So you might think that giving the LLM like a ton of information would help it give better answers.
Yeah.
But the research suggests that there's a point where adding more documents doesn't actually make the answers any better.
Oh, interesting.
Yeah. And it could even make them worse.
What?
Yeah. So they found that using at least a few relevant documents
Uh-huh.
is way better than just using the LLM's own knowledge,
Okay.
like a closed book scenario.
Right.
But then they looked at how the number of documents, which they call K, affects the accuracy of the answers.
Okay.
And they found that the accuracy kind of plateaus.
Plateaus.
Yeah, like it stops getting better after a certain point.
So like adding more documents beyond that point doesn't help.
Exactly. Doesn't help.
Wow.
So for one of the models they tested, called Mistral,
Okay.
the performance leveled off after about 5 to 10 documents.
5 to 10.
Yeah. But for another model they tested called LeMay, it's a little different.
Oh,
On some data sets, the optimal number was 4 or 5 documents.
okay.
But on another data set, it was 10.
So it kind of depends on the model and the data set.
Yeah, it seems like it.
That's fascinating.
And the researchers think that this difference might be because of the size of the model's context window,
Context window.
which is basically how much text the model can process at once.
So it's like if you try to read too many books at the same time,
Right.
you might miss important details.
Exactly. You get overwhelmed.
Yeah, totally.
You can only hold so much information in your head at once.
Makes sense. What about when they were testing the attributed QA part,
Yeah.
where the models had to cite their sources?
Right.
Did the ideal number of documents change for that?
Yeah, it did, actually.
Yeah.
And it's really interesting.
Oh.
So they looked at two main things: citation recall and citation precision.
Okay.
Citation recall is how often the model actually cites a document that supports its answer.
Okay, so like, is it actually using real sources?
Exactly. And citation precision is how many of the cited documents are actually necessary.
Oh, so like, is it citing too many things?
Exactly. Is it being efficient with its citations?
I see.
And what they found was that citation recall often peaks around the same number of documents as overall answer accuracy.
Oh.
But citation precision tends to peak at a lower number of documents.
So if you give the model too many documents,
Yeah.
it might start citing things that aren't really relevant.
Right. It's like oversighting just to be safe.
Yeah, like in a school paper.
Exactly. Like trying to impress the teacher with a long bibliography,
Exactly.
even if you didn't really use all those sources.
That's funny. They also found something interesting about where the best documents tend to rank in the results, right?
Yes, they did.
Mhm.
This is really important.
Oh, is it?
So they called the documents that actually contain the answer the gold document.
A gold document.
Yeah, the most valuable ones.
Okay.
And they found that these gold documents were often ranked somewhere between 7th and 13th in the list of results.
Wow. So not always at the top.
Yeah, not always at the top.
That's surprising.
It is surprising. It suggests that if we just take the top few results, we might be missing out on some really important information.
So we need to look deeper.
Exactly. We need to dig a little deeper.
This brings us to those gold documents you mentioned.
Yes.
How much of a difference do they actually make in getting a good answer?
They make a huge difference.
Really?
They're crucial. The research showed that even if just one gold document,
It's just one.
just one, is included in the information given to the LLM,
Uh-huh.
the accuracy of the answers goes way up.
Wow. So it's like the key ingredient.
Exactly the key ingredient.
That's amazing.
And this was true for both Mistral and Llama.
Yes, for both model.
And other researchers have found similar things.
Yeah, it's a pretty consistent finding.
So what happens if you have more than one gold document?
Well, generally speaking, more gold documents mean better answers.
Okay.
But just like with the overall number of documents,
Yeah.
the improvement kind of levels off after a while. So there's a limit.
There's a limit.
It's not like an infinite improvement.
Right, exactly.
So getting those gold documents is really important.
Absolutely essential.
But searching through massive amounts of data to find them can take a lot of time and computing power.
It can.
And that's where approximate nearest neighbor search, or ANN search, comes in, right?
You got it. That's where ANN search comes in.
Can you explain that a little bit?
Sure. So these systems represent documents and questions as vectors,
Vectors.
which are basically like points in a high-dimensional space.
High-dimensional space.
Yeah, it's a little abstract. But basically, each document has a unique set of coordinates.
Okay.
And the retriever is trying to find the documents that are closest to the question in this space.
So the documents that are most similar.
Exactly.
Got it.
But the problem is that finding the absolute closest match can be really slow,
Oh, I see.
especially when you have millions or billions of documents.
Yeah, that makes sense.
So ANN search is a way to speed things up.
Okay.
It's like a shortcut.
How does it work?
Instead of trying to find the absolute closest match,
Yeah.
it finds a really good match that's close enough.
Okay, so it's like sacrificing a little bit of accuracy for speed.
Exactly, a trade-off between speed and accuracy.
That makes sense. So what did the researchers find about how this trade-off affects the overall performance of rgraph?
Well, this is where it gets really interesting.
Yeah.
They found that even if you significantly lower the accuracy of the ANN search,
Uh-huh.
the overall question answering performance doesn't suffer too much.
Really? That's surprising.
It is surprising. For example, they lowered the search recall at 10,
Search recall at 10.
which is a measure of how many of the top 10 closest matches the search actually finds.
Okay.
They lowered it to 0.7,
Okay.
which is a pretty big drop in accuracy.
Yeah.
But the number of gold documents they retrieved only went down by about 2 or 3%.
That's not bad at all.
Not bad at all.
So it seems like using a faster, less accurate search method could be a good option.
It could be, especially if you're worried about speed and efficiency.
Right.
But there is a trade-off.
What's that?
While the overall question answering performance wasn't affected too much,
Yeah.
the citation metrics did go down a bit.
Oh, so the model was less able to cite its sources accurately?
Exactly.
That makes sense if it's not finding all the relevant documents.
Right, because some of those documents might be the ones that would have provided the best support for its answers.
So it's a balancing act.
It is a balancing act.
Yeah.
You have to decide how important speed is versus how important citation accuracy is.
Okay, that makes sense. Now, what about the opposite problem? What happens if the retriever finds documents that aren't actually relevant to the question?
Oh, that's a good question. And it's something they looked at, too.
Okay.
They call these irrelevant documents noisy documents.
Noisy documents.
Yeah, like they're adding noise to the signal.
I like that analogy.
And what they found was that adding these noisy documents generally made the answers worse.
Okay, that makes sense.
And it also made the citations worse.
Right, because the model might start citing those irrelevant sources.
Exactly. It's like trying to write a research paper and you accidentally include some random articles that have nothing to do with your topic.
Yeah, it's just going to confuse things.
It's going to confuse things.
But this contradicts a finding from an earlier study, right?
You're right.
It does.
What did that study say?
So that study suggested that adding a few random documents,
Random documents.
yeah, completely random,
Wow.
could actually improve the performance.
Really?
Yeah, it was a strange finding.
That's so counterintuitive.
It is, but this new research didn't find any evidence to support that.
Oh.
In fact, the results showed the opposite.
So adding irrelevant information is generally bad.
Generally bad.
Okay, good to know. They also looked at whether the similarity of the noisy documents mattered, right?
Yeah, they did. They wanted to know if noisy documents that were more similar to the question
Uh-huh.
were more harmful than noisy documents that were less similar.
Interesting. And what did they find?
They didn't find a clear pattern. So it seems like any kind of irrelevant information is bad.
That's what it seems like.
Okay, so just to recap, what are the main takeaways from this research for someone who's building or using Radke systems?
All right, so the main takeaways are,
Yeah.
first of all, getting those gold documents is absolutely crucial.
The gold document.
The ones that actually contain the answer.
Got it.
If you can get those into the LLM's context,
Uh-huh.
you're going to get much better results.
Okay.
Second, you can probably sacrifice some accuracy in your ANN search
Okay.
in order to speed things up.
So prioritize speed.
Prioritize speed.
That's good to know, especially if you're working with a lot of data.
Right. If you have a massive data set,
Yeah.
you don't want to be waiting forever for the search to finish.
Right.
But just be aware that this might slightly reduce the accuracy of your citations.
Okay, so it's a trade-off.
It's a trade-off.
And finally,
Yes.
avoid giving the LLM irrelevant information.
Avoid it at all costs.
Noisy documents are bad.
Noisy documents are bad. They're just going to distract the model and make the answers worse.
So it's all about finding the right balance.
Finding the right balance.
Speed, accuracy, relevance.
Exactly.
This has been super helpful.
Glad to hear it.
I feel like I have a much better understanding of how RAG works now,
That's great.
and especially the importance of the retriever.
It's often overlooked.
Yeah, it's like the unsung hero of RAG.
It is. It really is.
So given all this, how should someone rethink their approach to building RAG systems?
That's a great question. I think the main thing is to really focus on optimizing the retriever.
Okay.
Make sure it's as good as it can be at finding those gold documents.
The gold documents.
Yeah, and filtering out the noisy ones.
Right.
Don't just throw a bunch of random information at the LLM and hope for the best.
Well, so be strategic.
Be strategic. Be thoughtful about what you're giving it.
That makes a lot of sense.
Yeah.
What are some of the next steps in this research area?
Well, there's a lot more to explore.
Like what?
Well, for one thing, we could look at different ways to measure the relevance of documents. Okay. Right now, we're mostly using these vector embeddings,
Yeah.
but there might be other ways to do it that are even better.
Interesting.
We can also explore different architectures for the retriever itself.
Okay.
Maybe there are other ways to design it that can improve its performance even further.
It sounds like there's a lot of potential here.
There is a lot of potential. RAG is a really exciting area of research.
It is,
Oh.
and it has a lot of practical applications.
Absolutely.
Well, this has been a fantastic deep dive.
Thanks for having me.
Thanks for joining us. I feel like we've just scratched the surface.
We have. There's so much more to learn.
But this has given us a great foundation.
A great foundation.
And a lot to think about.
Exactly.
So thanks again for sharing your expertise.
My pleasure.
And thanks to everyone for listening.
Thanks, everyone.
We'll see you next time on The Deep Dive.
See you later.
Bye.